Welcome everybody to the first Passive House Massachusetts monthly meeting of 2025. We're excited to see you all here in person and everyone who's joining us on Zoom. This event, like all of our monthly meetings, is generously sponsored by MassSave and the sponsors of MassSave. And I'd like to just briefly share some information about the exciting Passive House related programming that they are offering this year. So there's single family incentives, which you can view here and which you can view on their website as well. And there's some really exciting multifamily incentives as well. Beyond base incentives, beyond Energy Star incentives, Passive House targeted incentives. And the thing I really want to point out is these large amounts per unit, $3,750 per unit. And these are incentives we hope will really promote a lot of passive house development in the state. We're happy to talk to you more about MassSave incentives and help you access them in your work. And there's also passive house adders along with these market transformation adders, and we really encourage you to dig into these programs and come to us or them if you want help doing so. So thank you very much to the sponsors of MassSave for making this programming possible. Thank you. We're really excited to have today with us John Deans of 475 Supply. John was previously a member of the Passive House main board and is a co-founder of Passive House Rhode Island, so he's got us surrounded. He's an experienced carpenter and he really knows his stuff, and we're really excited to have him join us and talk to us about foam-free construction. So, thank you so much, John.
Thanks.
Let's have a round of applause for John.
Oh, thank you. Is this the best spot for me to be?
You be wherever you want to be. This will find you.
Okay. Oh, that's weird. It's like presenting to the NSA, except you people are wonderful. All right. So, gonna do some quick introductory stuff. My goal here is to go through this very rapidly and as fast as possible, with the trust that you will stop me if I say something you don't understand or you have a question about something. Please stop me. But I'm just going to try to roll through it so that we have some time for questions at the end. That's me again. I also have business cards here and whatnot. You can get my contact information. So. I used to have slides about some of my work and experience, but this is actually my dad. He is a retired shop teacher, so I kind of come by this world a little honestly. And he teaches an adult ed class now, so he's teaching folks how to do basic woodworking, and they made him cupcakes with sawdust on them. Edible, I believe, but still pretty clever. But in many ways, this explains me better than anything else, because ever since I was a kid, I was making things. My brother and I built forts, and my dad was on and off a carpenter and an educator, and so we would go to job sites on the weekend and gather up the form nails from the concrete work and bend them straight, and that was what we had to use for our projects. So my hands have always been in making things, and then fast forwarding, I went to College Atlantic in Bar Harbor, Maine, and studied human ecology. My sort of roots as a professional are more actually in activism, and I worked at Greenpeace for 9 years. So I worked on various climate and energy, toxic chemical campaigns and whatnot, and then about 7 years ago transitioned to high performance building, and then I've been with 475 for about a year. So that's the quick on me. That's just some projects that I worked on. I'm going to run through just 475 for those who aren't familiar. We're a high-performance building supply company. We focus on sort of unique envelope solutions. So we have a whole line of tapes and membranes for air sealing, flashing, from a German company called Proclima. We're the exclusive distributor for them. We have a couple of ventilation solutions, Lunos through-wall HRVs and Brink ERVs. We are still selling Gutex wood fiberboard for exterior insulation. At some point, Timber HP is probably going to catch up with us, but for now, we're still supplying that to the market. We have some skylight solutions that are high performance, well insulated, well air sealed, insulated curves integrated. So we kind of are looking at the whole envelope and making sure that we're offering solutions for all the sort of unique parts of it that we didn't see in the market. And I skipped over these slides, but this presentation is sort of an embodiment of the fact that a lot of times I look at 475 as sort of a knowledge resource company that sells a lot of tape. So a lot of what we are as a mission-driven company is into education, doing presentations, but also if you go to our website, it's very rich with information, including our smart enclosure that goes through a lot of these different types of assemblies. So tonight, ignore all this AIA stuff because it's just integrated in my presentation, but Passive House Massachusetts will be handling this. We're going to be talking about foam-free, airtight, resilient construction. So what is high performance? This is kind of how we think about it. It's comfortable, it's healthy, energy efficient, resilient, and beautiful. We want nice spaces to be in, we want nice buildings in our communities. So these are some really basic things to try to achieve in principle, but getting there can be a little bit difficult. This is one of our co-founders' kids next to a window in winter in Brooklyn with their socks off, and they're totally comfortable and warm. And this sort of always embodies for me like what we really mean by comfort, that you just feel at ease no matter where you are in your home. Looking at high performance as an integrated system. So it's all these components together. It's not sort of like this piece over here, that piece over there, but looking at how windows and the envelope and ventilation systems, heating and cooling all work together. To achieve these, we need a robust enclosure, quality daylighting, less toxic, more sustainable materials, healthy indoor air, durability. That's a big one personally for me. Is I want these buildings to last and be functional for a very long time, and zero energy ready. And the point of that is to support the transition to renewables. So I won't be talking actually too much about foam itself, but just a little bit of an overview of kind of our perspective on foam. It's often been looked at as an air barrier over the years, and we're really sort of strongly opinionated that it's not a great air barrier because it's not reliable, and these pictures sort of show you the problems that you can encounter. So over there, that's a picture from one of our clients where the spray foam in the wall just completely crumbled and fell apart for whatever reason. You can have the situation where it pulls away, or even where the wood is saturated during construction and then dries out and shrinks away from the spray foam. So now we have cracks that are a problem. It's not airtight anymore. And the foam itself, even though it's relatively stable, you can, particularly like with foam board, which is this article, it can expand and contract, and so it can create voids and not fully continuous insulation. I kind of look at it like you're trying to do advanced chemistry in the back of a box truck. And there are some folks who get it right. There are some folks who do a really good job with it. But you can have spray foam that looks really good on the surface, but actually didn't get its chemical cure right. So now it's not even giving you the R value that the building is designed around. And when we're designing these high performance envelopes, like passive houses, everything relies on all of the assembly working the way it's designed to. So if you have some part that's sort of failed in the system, you're not going to have the level of efficiency and maybe not even the levels of health. It's also, foam products tend to have high embodied carbon. So if there are questions about what embodied carbon is, please shout those out. I'm just going to make the assumption folks know. If you don't, that's cool. I'm happy to get into it. But essentially, you're starting off with a debt to the climate, is how I look at it. Whereas if you use biogenic materials, wool, cellulose, cork, wood fiber, those things are going to start you off in a place where you're actually storing carbon. Use a bunch of toxic, nasty stuff. Both in the production, but even on site, and there's off-gassing, so there's a health risk with it. But I said I worked at Greenpeace for a number of years. I worked on toxic chemical gas disasters for about 4 years. So I spent 4 years of my life talking to communities who live around the facilities that are producing this for us. They don't love it, right? They've got higher cancer rates. They live with the risk of these gas disasters. It's not a nice environment. And so part of it is remembering that the choices that we make have downstream effects and upstream effects. This is me in Freeport, Texas, outside of a Dow chemical facility that makes phosgene, one of the precursors to a lot of foam products. And then if it's not done right, you can have disasters like this. This is from a new construction where there was spontaneous combustion because the environment and the mix wasn't right, and you know, the product actually burned down brand new constructed buildings. So there are risks associated with it. We take risks all the time in life, right? Risks in and of themselves aren't necessarily, you know, a bad thing, or they're oftentimes necessary, but when they're not necessary, it's best to avoid them, right? And so that's kind of how we look at it, is that it's effective in a lot of ways, but foam isn't necessary for a lot of the things that we're using it for. Yes, please.
I'm sorry, can you go back to that slide? I just had an embodied carbon question about a wood fiber. Where is that under?
Yeah, wood fiber you can just sort of imagine would be down with sort of dense packed cellulose.
Okay.
in that range, depending on the forest it comes from and whether it's FSC certified and a few other factors. I mean, that can vacillate, but you're still starting out in a positive direction with wood fiber.
All right.
As an example, the Gutex wood fiber insulation, even though it comes from Germany, is still carbon neutral by the time it gets here, even with all the shipping costs involved. So we don't, you know, like I was saying, we don't need it. We can make more robust, resilient, sustainable, higher performance homes without foam. To sort of establish a little bit of a baseline for that, I'm going to go through some sort of basic building science, you know, aspects that sort of influence this. And you know, the main control layers, we learned this in Passive House, but also just general building science, water control, bulk water, air control layers, vapor control layer, and thermal control, right? And I always think about them in this order of importance, right? We've got to get bulk water away from the house. That is essential. If it was an airtight, well vapor controlled, good thermal envelope, but it floods all the time, we're not loving that, right? I'd rather have an airtight house that has good vapor control and crappy insulation. I want all of it. But when we think about the priorities and we think about how to think through the system, this is sort of how we organize it. This one's hopefully relatively simple, although I was having conversations this week about folks who are like, we really need to teach people how to flash properly. So, you know, constant battles, right? But we need to get the water away from the building. We need to shed it with our masonry buildings. We got to make them bumpy so the water kicks off and doesn't just sort of absorb in as much as we can help it. Air control, this has become, well, currently, and just probably for the rest of our known lives, we're going to be dealing with this. We're just increasing the amount of pollutants and whatnot in our air, and so I think we've all become more conscious of the need for good indoor air quality. Vapor control is, you know, this isn't, you know, because the sheathing flooded from the outside. This is that the water got trapped on the inside and the sheathing rotted, right? So now that's not just a health problem because we can see all that mold, not just an energy problem, but now it's a structural problem, right? So we want to try to avoid those things. And we want good thermal control. We're going to go all these in more depth. So just a reminder, happy to get into this more if folks have questions, but I'm going to skip through and just say we got to have good flashing, right? You got to think about how gravity and water work, but also you have to think about how wind and water work, and we got to make sure that things don't get blown into places they're not supposed to be, and that water is shed away from the building and isn't sort of put down behind something else. This is one approach to helping with those systems is monopoly framing. Make sure you've got a really good continuous water control layer, and then you can put on the more aesthetic features. Rain screens, so having a proper rain screen and vent channel on the walls, but also the roofs of the buildings. We're a really big fan of vented roof assemblies. Again, it allows you to use bio-based, lower carbon, vapor open insulation. If you don't have a vented roof, you have to use a vapor impermeable insulation. What's that going to be? It's going to be foam. So we want to see a vented roof for that application, walls as well, just allowing these buildings to dry. In terms of WRBs, there's kind of two major ones in the market. There are sort of monolithic ones where it is a chemical chain diffusion. So literally, you know, if it's drier on this side of the membrane and the water's on this side, the vapor will just sort of get attracted and go through on a chemical chain through the membrane. And then there's microporous, where they sort of stretch the polymer and create all these micro tears in it. And so it's a little bit more like a microscopic colander, where the holes are small enough that bulk water can't really get through, but vapor can make its way through. And those operate more on like a vapor pressure diffusion gradient. So you need a little bit more of a gradient on either side to sort of force those water molecules through. So both waterproof, vapor open membranes, but those are the basic technologies that are out there, aside from like your tar paper, old school tar paper. All right, no matter the size of the building, we need them to be airtight. We need, and really, I like this term, air control. It's about controlling the air. Making them airtight is part of that, but it's also about us deciding where the air comes in. I spend a lot of time on job sites, talk to a lot of old school carpenters, house gotta breathe. I agree, let's give it a set of lungs, and let's control where it breathes in and out, right? Not through its skin. Buildings aren't frogs. Oh, that was delayed, guys, but I'm glad that you got me there. So this is just an image to kind of show, we want to see the air tightness inside and outside of the envelope. These are kind of just showing the different layers that can be involved in that. Does anybody not know what that is a picture of? Totally fine if you don't. Yeah, perfect. That is a blower door. This is how we test the air tightness of the building. So, giant fan. These are sort of plastic rings that you can change the size of. And essentially what you can do is pressurize the house or depressurize the house. And with the manometer, you can figure out how many cubic feet per minute of leakage you have. And that's how you test the leakiness of the envelope. We bring this up because we think it's important to view this not as a final test, not as a did I pass, but as a diagnostic tool and a part of the construction process. Having ideally multiple blower door tests throughout to test your shell, to test after insulation, or maybe an interior air barrier's been added, to make sure that as you go, you're remaining airtight so that you don't get to the end of class and then suddenly realize now we have to take apart the wall to go find an air leak. So treating it as a tool in the process rather than just your final test. There's two basic ways that we see the air test. The code, I think in Massachusetts is ACH 50. So that's air changes per hour at 50 pascals of pressurization or depressurization. So that's looking at the volume of air, how much of that is leaking through the envelope in that period of time. The surface area leakage, cubic feet per minute at 50 pascals per square foot, is really looking at the integrity of the envelope itself and how much of that surface area is open for leakage. And so in the passive house world, this would be PHI, and then the surface area would be FIAS. So two different ways to measure air leakage. And we're not going to argue tonight about which one's right. I won't have it. So one of the reasons why air control is important is connected to vapor, right? So there's vapor diffusion, and this is a study from Builder's Guide for Cold Climates from the Building Science Corps. This is old. I've actually heard recently that this may not be 100% accurate, but the principle still stands. We may be changing the slide, but with the actual numbers, but the principle still stands that you have far less diffusion through a sheet of a 4x8 sheet of gypsum wallboard, right? About a third of a quart of water. It's a measurable amount. That is moisture that is getting into your assembly. But it's not necessarily a crazy amount, whereas a 1-inch hole in that sheet is 30 quarts of water This number may not be 100%, but it is way more. So that's the important thing here. It is way more moisture that can travel on an air current over the course of the heating season. So this is why airtightness is important, because we're gonna have vapor diffusion through most of these materials, but we can control how many holes we have in the envelope, right? This is my water break, but just another way to visualize the amount. It's like dumping those behind a 4x8 sheet of drywall over the course of a winter heating season. So we talked about diffusion. It's also, yes, these slides will be available after the webinar. Thank you for asking that, Monica. I think this is one thing that I didn't think about even when I was building for a really long time, but our buildings start off wet, right? Every building starts off, especially in a relatively moist climate like ours. So we just have to think about that and think about what we're doing to manage the moisture that's already inherent in the building when we close everything up. Capillary action, thinking about things that are sort of stuck into our envelope, like masonry, for instance, that are wicking moisture into these places. And then air infiltration. This also kind of shows you sort of a little bit of moisture, a little bit more moisture, maybe a little bit more moisture, a lot of moisture, right? Just hammering home the point of airtightness. Another reason is thermal bypass. So this is these sort of images. There's a bunch of different ways that this can happen, but the idea here is, like, if we look at that spray foam picture from before, we had cracks on the side, right? Or if you think about poorly installed bat insulation, and you have a crack next to it, it's not totally tight in there, and you have an air leak. Now you have air whooshing by the insulation, so your insulation's not doing what it's supposed to do anymore. Your R value is now plummeted, and now you have, in the wintertime, warm, moist air moving in there and wanting to condense on sheathing. And you can create these convection loops in the wall itself, where you're mixing that air and your insulation's not doing its job anymore, and you have these potential moisture issues. Yeah, so a large amount of wind washing can deplete your R value by like 90%. So this is a study that kind of gets into what a large amount is, but just, again, in general terms, it can have a big impact. You thought thermal bridging was bad. Does anybody recognize this building?
No.
I didn't. I just gave the presentation, so I know. This is the first passive house in Germany, Darmstadt. So what if we take this house that we know is good, we know it's designed well, I know it's engineered to use a low amount of energy. What happens if we model it and all we change in the model is air tightness, right? If that building is 5 ACH50, 12,000 kilobTUs per square foot per year, right? If we drop that by 2 ACH50, we get about a 34% reduction in energy use. Go down to the DOE Zero Energy Ready, and we've got 5,000 kilobTU, so we've got a 61% increase in efficiency. And then the PHI, Passive House Standard, of 0.6 ACH50, we've dropped the energy use of the building by 87%. That's just airtightness, right? So again, this is why we think about these in terms of priority and why airtightness is so important in these buildings. And it's got to be continuous, right? So the old exercise is, if you're drawing a design, you never pick up your pencil to trace the air barrier. It's connected everywhere in the home. We need continuity of that, because the moment you interrupt it, that's an air leak. And the materials that form the air barrier should be robust. So drywall, not a great air barrier, because that can happen. We also know our buildings get renovated all the time. So if we're thinking about building out 100, 200 years, we know there's going to be renovations, and this is the walls. The wall that we see, that's the sacrificial layer. That's the one that's going to get torn into. That's the one that's going to have cabinets put on it, holes put in it. We can't have that be our air barrier, the part that's going to be sacrificed throughout the life of the building. And, you know, things like masonry, like this is a situation, like this is a particular type of OSB, I don't know which one, but these were tests where plastic was put and taped on and air sealed to these surfaces, and then they did a blower door test, and you can see it billowing. It's sucking air through the OSB, right? It's not through cracks in the OSB, everything's been taped. It's all really, look at, that's beautiful air sealing work, but the material itself isn't a robust air barrier. So we have to think about those things when we're doing material selection. There it is. You know, caulkings will work for a period of time, but we find that they fail over time, right? Things move and move and move and move, and then eventually we see the degradation in those materials where we see this more and more. This is why, you know, people talk a lot about tapes. I sell tape for a living, but tapes are really important because the adhesive technology is better, it's going to last longer. The tapes are going to allow some pliability and allow that movement to occur over time without actually interrupting that air seal. And then interior walls, you know, this is a membrane that has been taped. It's taped to the slab, I think in this case. It's taped to the ceiling air barrier. We can see where the air barrier is here. And we'll talk about this a little more in a second, but also you can see all of the strapping on the ceiling and walls is making it so that that sacrificial layer is now out away from our air barrier. So our air barrier is back in a protected location. The other aspect of this is, in this case, this air barrier was installed, this strapping was installed, and then the interior walls were put in. So that in places like this, where you have a junction of, you know, a 90-degree interface of that partition wall with the exterior wall, that air barrier is continuous behind it. You're not interrupted there, right? Another way you can approach this is you can just put a scrap of air barrier material in that place, and then you can come back later. You know, because a lot of times our framers just want to frame, they want to get the whole thing framed at once. It's just about taking that extra little step to think ahead and say, okay, let's put something here so we can come back to it later and connect that air barrier. This is another approach that you can do, same kind of idea. We haven't trademarked the term, but at 475 we like to call them floppy bits. Very technical. You got to put a floppy bit in there. So in this case, the floppy bit is you frame your first floor wall, let's say. You put a floppy bit, which is the dotted line there is representing like a membrane of some kind, WRB, an interior air barrier membrane. And then you put your floor system on top of it, you wrap that membrane back up, and then you set the second floor wall on it. Super easy way to ensure that continuity between the first and second floor and make sure that you maintain airtightness. But it takes that extra step of thinking, okay, before we put the floor system on, we got to give it our floppy bits. Sealing both sides of the window, so flashing on the exterior, but also trying to keep the exterior as airtight as possible. But also taping on the inside of the window for air tightness to make sure that that air barrier is continuous. We can pre-tape windows. So this is again about sequencing and thinking ahead. Rather than trying to sort of slip a piece of tape in after the fact, we can pre-tape the window, put the window in the hole, peel the backer off, stick the tape in, and it's all done. It takes a little bit of, you know, forethought and a little bit of care when you're putting it in, not to sort of tear things up, but it can make the whole process a lot faster and easier. Penetrations, wires, conduit, pipes, you know, using gaskets or like liquid flashing or various stretchy tapes, but making sure that our penetrations are sealed on the air barrier side and the water control layer. So this kind of gets back to that sort of wind washing idea, but it's also just in general, these are the dynamics of you know, air movement. You know, wintertime, we've got a warm interior, cold exterior. And so again, like if we have an air leak, it's going to go through the insulation, and that you can see the droplets of water there condensing. Now we have bulk water in our wall, started off as vapor, turned into bulk water. So it's either got to turn back into vapor and dry through, or it's got to soak, or in many cases, it's just going to sit there and provide a nice habitat for mold. So if we put our interior air barrier on the inside, we can keep that warm, moist air from getting into the cavity in the first place. This gets back to that service cavity idea where we put our air barrier back in a protected location, but this is what it can look like, where you can run your utilities in that cavity so they don't even have to go inside of the air barrier to the outside. Again, thinking through a renovation scenario, people tear walls apart, but then they want to change their wiring, they want to change where the water fixtures are going, whatever it is, it's right there for them. They don't have to dig into the air barrier in the future. So vapor control, we've touched on it a bit, but this is how we used to do things. Actually pretty good from a building science standpoint. Just put a big jet engine inside a brick building and bake it dry. Make it super leaky, superheat it, put all the heat through to the outside, warm the street, and in the process you dry your building. It's awesome, works great. Happens to be horribly inefficient, but it works. So now we're making these airtight buildings, so where's all the vapor going? Right, now we have to manage that vapor. Again, this is about controlling these factors. So we sort of created a new problem for ourselves that we now have to attend to. Talked about that. It's the reverse in the summer. We've got warm, moist air outside. We've got cooler, drier air inside. Vapor's going to want to drive in. So we want our building to be able to dry to the inside as well. This is just another thing where foam gets in the way. So it's an impermeable material, and so it's going to make it so we can really only dry to the inside. So our drying time is just going to be in the summer when it's cold, cooler and drier inside. We don't have that drying to the exterior now. We've blocked it. We put a dam in the way, or a vapor trap. And this is what can happen, right? We're going to trap moisture into these places. It can maybe sneak past foam in these little cracks as vapor, and then condense, turn into water. Now it's not going to dry in the same way. Using vapor open materials, in this case, like plywood is more vapor open than OSB, for instance. Using vapor open weather resistant barriers. We'll get to some of those things. Thanks for I'm trying to keep track of the chat here, but yes, ventilation is a key part of this, right? So, some other ways to think about our assemblies. Maybe we move the sheathing towards the inside more. Put a big insulation cavity on the outside. Use a membrane, that's vapor open as a WRB, but the insulation's right behind it. Everything can dry really nicely. Your potential condensing surface is now way inside the building. These are Larson trusses of various forms. This one's I-joist outrigger, and this is a more like DIY Larson truss. So when we talk about this interior vapor control layer, it needs to do a couple of things, right? We're asking it to keep the fusion, we're asking it to be airtight, but we're also asking it to keep moisture from diffusing into the wall. But if moisture's in the wall, we need it to be able to dry out. So we need these smart vapor retarders, these vapor variable materials on that side, because probably a lot of us have seen sort of old school method of using like a poly vapor barrier on the inside behind the sheetrock, and it causes rot because it does a really good job of keeping the moisture from being able to dry.
How does paint play with that?
So paint is going to help you with being a vapor retarder. So a couple of coats of latex paint, for instance, are going to help with some of that, but they're not necessarily going to be continuous because you're going to have these penetrations around boxes and stuff. So now we're talking about airtightness. So you get a little bit of vapor diffusion control, but you sort of don't have that airtightness with it. And it will allow drying as well. But it's not vapor variable so much as it kind of has its own perm rating. So this is just looking at kind of like the difference in perm ratings, OSB. Again, we're not going to argue tonight. This sort of ranges all over the place, but let's say it's around 2 perms. CDX plywood, 8 perms, I've seen it go up as far as like 13. And the higher the perm, the more vapor open it is. And vapor variable membranes that start relatively impermeable, but open up as they respond to relative humidity. And then smart vapor variable membranes that do the same sort of thing, but have a wider range of permeability and a different vapor curve, which we'll get into. Just gonna skip that. So this is what like the vapor curve looks like for a smart vapor retarder, where you have, you know, you're sort of below 1 perm until you start hitting this sort of 60 to 70% area, which again, there's a bunch of different ASHRAE formulas for like when mold might grow. But generally speaking, when you're above 70% relative humidity, you've got a good environment for mold growth. So that's when those membranes start opening up and really allowing that drying to occur, to avoid that. Is anybody monitoring the chat in here? I keep seeing it pop up. Are there any
Yes.
questions that I should get to?
I am monitoring it. No, we're good.
Okay,
I'll let you know.
all right. I'm happy to get to some questions at the end too. This is looking at sort of, again, we talked about construction being wet, right? So this is looking at a model where we start off with, you know, this higher water content in the materials in the wall itself, and what we want to see happen over the years is that sort of dry out and then stabilize, right? If you have, you know, if you had OSB or polyethylene sheet that we talked about, the old school poly vapor barriers in the walls, it never really dries out. So you trap that moisture in there from construction. You know, your wet construction stays wet. With a vapor variable membrane, you're going to get some of that drying and then it's going to sort of level off. And this is sort of the push and pull of the seasonal cycles of vapor, right, over these years. And then a smart vapor variable membrane, you're going to get it much drier and it's going to stabilize at a much lower moisture level. So thermal control, you know, thermal bridging, hopefully folks are familiar, happy to get into it if you're not, but this is sort of like this is just kind of an impactful image of like what it can look like, how much heat can be bleeding out through your structure. You might have awesome R values, but if you've got tons of thermal bridging, you've got this conductive heat loss through the structure. So this happens to be a thing where you can break up like a slab in a tall building like this, so you can basically make a separation between the interior structural concrete and the exterior balcony, and there's a thermal break in the middle of it. Oh, but that happens. The developers in the back of the room are laughing. Again, just going to kind of zip through this, but this is the sort of change you can see in that kind of scenario. So we've shifted where that sort of thermal line is. And then ideally having vapor open insulation too, particularly on the inside. So this is looking at like a masonry situation where you want that brick to be able to dry, you want the cavity to be able to dry. So using the vapor open materials like wood fiber, you know, cellulose, mineral wool, those kinds of things. And then on the exterior as well. So we got mineral wool over here, we got wood fiber over here, both vapor open exterior insulation, so we don't have that vapor trap problem, right? So we're keeping our sheathing warm, which is great, and then we're also allowing drying to occur. So just quick summary, make it tight, continuous control layers, minimize the use of foams. We understand too that particularly in a lot of retrofit scenarios, sometimes foam is avoidable. It is the best product for certain things, but try to minimize or eliminate it. Use a blower door as an actual diagnostic tool, and protect your control layers. Make sure that air barrier is in a protected location in one way, shape, or form. So I think that's the end of it. And like I said, I raced through it with the hope that maybe we have a little bit of a conversation and some questions. So do we have some to start with on the chat?
Well, first, before we get into the chat, I just want to say thank you so much.
yeah, sure.
Thank you.
Thanks.
And we'll bring this down so we can see the chat.
Oh,
Stop
perfect.
sharing.
There you go.
So we can see folks here, and they can see the whole room. Also, I'll just make a brief announcement that if you're looking for CEUs online, Beth is going to post the link in the chat there for people soon. And there is a QR code out here for people who are here. It's also a sign-in sheet, so if you register, you can check your name off here, and I'll pass this around. And with that, yeah, we can take a question from chat, and then we can take a question from the room, and I'll let you manage that.
Sure, yeah. What do we got, Beth?
Check.
Can't really.
So there's a comment, there was some pretty harsh statements about foam in the beginning.
Yeah.
But then the slides mostly showed spray foam in interior cavities. It seems incomplete to overlook the benefits of exterior foam continuous insulation.
Mhm.
Couldn't that strategy meet the need for airtightness and vapor control?
Yeah, so we talked about, part of the problem with exterior foam, and again, it's sort of from a building science standpoint, you keep your sheathing warmer with an exterior foam, hopefully you don't have those condensation issues. But we're really promoting like an assembly that can fully dry. So again, we look at that foam as a potential vapor trap. Can it be airtight? Absolutely, it can be airtight. Particularly, you're not relying on the foam for airtightness, it's really just that R value, that thermal control layer. So certainly that, we're not saying that it can't be done, we're saying that it's not necessary. Again, that's kind of like our perspective. So we certainly see that in plenty of places. Foam is very ubiquitously used, and safely so, but it doesn't mean that it is the only solution, and we think there are better ones. Hopefully that answers that.
Great, and then there is another question that came up. What are your thoughts about installing spray foam to provide an air barrier on the interior side of existing masonry walls in retrofits?
Yeah, we don't love it again because the same kind of concept is that it's unreliable. We've seen it fail a bunch. It can pull away, it can crack, you can have those continuity issues. So as an air barrier itself, I don't love it there. If you were using spray foam on masonry, I would encourage either using a continuous lime plaster coat on the inside of that masonry as your air control layer, or a liquid applied membrane. There's a bunch of them out there. 475, we happen to sell one, but like having something that you know is continuous and you know is stable and going to stay there over time. And then if spray foam is the specification and that has to go there, treat it as a thermal control layer, not as the airtight layer.
Great, next question. Is there any long-term data about how variable vapor variable membranes are over multiple years? Understand it is a newer product.
Yeah, so it's always this thing in the industry where, we do this with so many products, right? There's lab testing and then there's real world testing. And real world testing has to take place over years, but all the companies producing these materials are putting them through like advanced age testing, UV testing, multiple like moisture tests. So they're tested to the extent that we have the lab technology to do that, just like any other material that's out there, with the anticipation of what they're going to do over time.
Great. Question from Massachusetts. Now that the building code has been updated, how can we approach vendors on this issue?
Vendors maybe being like subcontractors or like building supply companies? Because either one.
Yeah, this is, Monica didn't say, so Monica, if you're still listening, if you want to clarify your question.
Yeah, I can kind of take a stab at it, and then if there's clarification, get into that. The way I think about it is, when you're building a high-performance home, whether you're an architect, the client, builder, subcontractor, from a practical standpoint, my experience building high-performance homes, it's a team thing, right? So I think having a team as early as possible that's going to take the project all the way through completion, and any associated vendors with those teammates are brought into the loop. So I think there's a communication side of this that really matters. It's sort of an intangible, but I think communication is key, because surprises lead to inefficiencies and bad assemblies and all those kinds of things. So I think a team orientation is part of it. I think like on the architecture side, I'm always encouraging architects to be as explicit as possible in the plans and really identify either the products or the product characteristics that are acceptable, and how they should be used and where they should be used, and really sort of drawing it out as explicitly as possible, making section details that really show where everything goes and how it's all connected. So I think, you know, having accountability built in from the get-go through the team structure and the plans themselves. On the homeowner side, it's about advocating for what you really want, and being really firm and saying, well, these are the materials that I want to use, these are materials I don't. And you have to sort of, it's your project, this is for you, and it's okay to own that. You want to defer to the experts in terms of the application of these things and how they get put into the design, but it's totally fine to be firm about what it is that you want. And I think on the builder side, which I engage with a lot of it's about just education. So like that's one of the things that like 475, like technically we're an e-commerce company and our storefront is our website and we sell all these products, but most of my day-to-day is spent talking to people over the phone, having Zoom meetings, doing site visits, meeting in offices, and kind of going through these things and helping to educate people who aren't as familiar. And we see that a lot in Massachusetts right now. Massachusetts is super exciting, and it makes me incredibly hopeful, because I've just spent the last year working with companies of all different shapes and sizes throughout Massachusetts who are coming to me saying, I've never seen these materials before, I've never seen these assemblies, I don't know what to do, there might be some fear, some skepticism, but the process of sort of education tends to neutralize all that and demystifying these things. So lean on the people like me who exist in the world and any other suppliers who might be involved in the project to help do that education and make sure that people understand the things that are being used.
Yeah, and she did clarify that she meant manufacturers in this case, because a lot of manufacturers aren't necessarily catering toward what Massachusetts specifically is requiring.
Yeah, I think at that point, it's about picking the manufacturers. Not all building materials are equal, they all have different attributes, so I think vetting the materials, and then, the longer term movement side of this is putting pressure on manufacturers you don't think are, fitting the bill. If they're not providing the materials that you think they could, try to get them to, try to create that demand. I think that's a longer road, but consumer advocacy can be part of this, right? We do vote with our dollars, especially when we're talking about projects that, nowadays are at least hundreds of thousands, but mostly, above $1 million. There's a lot of money being spent on these things, so that does carry a vote.
We can also take questions from inside the room as well.
Yeah.
People have questions here.
Yeah, please.
One of the things you said in the, I think it was the air barrier section, you prefer an air control layer that can double as the vapor control layer, and it's always better if it's on the inside. I almost exclusively work on commercial buildings, large multifamily or not even residential. Do you see that type of construction in the commercial world, and how does that play out with like compartmentalization requirements on a multifamily house with an interior air barrier?
Yeah, that's a great question. I do see it a lot more now. That there are things that is one of the things that I do see VE'd out, but I see it less, I think, than it has been, because I think people are understanding the value of it and these assemblies are changing. Part of it too is, in commercial construction as an example, you usually have less R value in the wall. So you do have a lot more of that like heating and drying effect. Now we're thickening those. So now this sort of vapor control and the airtight layer has become a little bit more of something that's under scrutiny. It doesn't mean that you can't have the exterior sheathing, for instance, be the air barrier. And like in a masonry application, you can use a coating on the back of the masonry that's going to be your airtight layer. and then have a separate layer on the inside that's maybe just acting as vapor control, because you have now a thicker, assembly. I've got like masonry, for instance, I've got a presentation similar to this, but is more specific about that. And you look at the different models of as you thicken the insulation, how your moisture risk increases, and sort of trying to find that sweet spot. So one of the big things that I encourage people to do is model this. All models are wrong, but some are useful, right? So it can help inform the project by being able to model these things and how they're going to work, and that can help you determine sort of where you need the control layers for a given design. Is that helpful?
Yeah, kind of.
Push me if you want, please.
I would say like we're almost always trying to maximize exterior insulation, and then if we need a better R value on the wall from an overall building's performance standpoint, and the wall is what we've targeted as the best option to upgrade. You're already at like maximum exterior cladding depth or maximum rain screen depth, and you say, okay, now we've got to go to the interior stud cavity that we weren't maybe on a non-passive house project. Oftentimes the debated topic is, do you want to rely on the detailing of a vapor control layer on the inside with a non-foam insulation compared to a close-up foam that doesn't require it? Yes, there's cost associated with material install of that, but if you're only it's all a parametric study, you're like playing with inches of insulation and looking at a sandwich and looking at, okay, what's my split, and then trying to find the ideal. And this kind of overall system configuration isn't always necessarily the driver as it is searching for maximizing R value and matching the basis of design construction that we were originally shooting for.
Sure. I mean, I think you're sort of describing the process that it takes to determine that. And so, I mean, if it's the more exterior insulation you have, the less that moisture risk is on a condensing surface, right? So, I mean, you have that going for you, but like you said, you have to play with those numbers and sort of where the dew point is moving and how much that matters. I mean, the best, our technical director, my boss, Aaron, basically always says the best assembly is the one where all the insulation's outside and the sheathing's on the inside, right? So whenever we start to get away from that, we start to encounter these problems. And again, I think that's where modeling can help. But I also think that a smart vapor control layer is never a bad idea. It's always going to help keep vapor from diffusing into the wall. It's always going to help with the air movement if it's installed airtight. And it's still always going to allow drying to the inboard side. So in some ways, it's one of the easiest things you can do to sort of make sure an assembly is going to be safe. But then there's obviously a material and labor cost associated with that. So, these are the kinds of things also that I'm happy to have meetings about and kind of go through these assemblies.
Yeah.
So hopefully that's helpful. Yeah, please.
Is there any general advice for when you would want to put a single family home? When you would want to put mental wrap on the outside versus Intello on the inside?
So Mento is going to be your vapor open watertight layer. So that's, at the very least, that's going to be on the outside for bulk water control. We also encourage it to be installed airtight, whether it ends up being your primary airtight layer or not. That depends project to project, but it's still going to help even if your primary air barrier is on the inside. Again, having airtightness on either side of the wall is going to help with that potential air movement. And then Intello sort of serves a separate purpose where it's helping to control vapor, but it can also be either your primary or another airtight layer on the inside. So you would have Intello inside, you'd have Mento on the outside. You could have Mento on the outside and no Intello inside, but typically you're not going to not have some kind of weather resistant barrier outside if you have Intello. Does that make sense? Does that not make sense?
Yeah, I know, it would be very expensive to have Mento on the outside and Intello on the inside.
Maybe. Yeah, I mean, I think this is where
And do you need it?
these cost issues. Do you need it?
Yeah.
I mean, again, I think it varies there's so many different assemblies,
Yeah.
that it varies. Like, for instance, I really highly encourage, a smart vapor control layer like IntelliPlus for a double stud wall. Because pretty much every accepted model sees that sheathing on the exterior side as being a potential condensing surface. There are folks that vehemently disagree with me on that point. You know, and there's a lot of, I think one of the things to remember.
We're not building that many double stud walls anymore, are they, in single family?
Yeah, people,
Oh,
Oh, they are?
I almost wanna say
It's still popular?
it's at least half, if not one of the most popular
Oh, really?
Yeah.
things to do, yeah.
Oh, okay, that's helpful for, I didn't know that, thank you.
Yep, and I think, again, the biggest advice I always give on a double stud wall is it better be airtight. Because we don't want moisture being able to move in on air current, right? You know, diffusion's the only thing we want to be battling at that point. And then it's a question of, are you looking at the model? Do you think drywall's gonna do it for you? And these are the conversations that happen all the time. And they go back and forth and people make different decisions. And I think one of the things to remember too is building science is a live issue, right? We are in the middle of massive social level tests in building science right now. And there's, like I said, like models will tell you some information, but it doesn't mean they're right. Because one aspect of a wall in a particular location might act differently than what the model says it's gonna do. And so one of the reasons I work for 475 and I promote these products and I like this methodology is because I'm risk averse when it comes to this stuff. I wanna build the most bomber assemblies that I know are gonna last a long time and have all the right parts and pieces. But it's a spectrum of risk that we're talking about. It's not sort of like an if-then. If you use this, then this will happen. If you don't use that, then that will happen.
Right.
It's more like, what level of risk are you willing to assume? You know?
I hate to ask this question.
Don't hate it.
So is there a lot of uncertainty with the vapor control layer? And the reason I ask this is because, so you were showing details where you have a membrane going up around the rim board. I've been on 5 passive house projects and I've never seen that length of detail. And I've asked the engineers, the architects, about the vapor control layer. It's always on the outside of the sheathing. So I've never seen it on all 5 projects on the inside face of the building.
Mm-hmm.
But every class and seminar, it's always shown on that inside face. And nobody's been able to explain it to me where I walk away going, I understand it now.
Well, some of this I think gets to the nomenclature too. So like when we look at different assemblies, your vapor control layer is basically kind of your least permeable section of the wall, right? And so if a building like you're talking about has a couple of coats of latex paint on drywall on the inside, that's your vapor control layer, effectively. Because everything, and if you have like cellulose and then CDX and then a vapor open, you know, membrane on the outside for weather protection, then you've got, you know, tons of vapor openness on the outside, and that's your vapor control on the
But
inside.
doesn't that defeat the whole purpose of continuity in terms of your interstitial spaces between floor and ceiling?
Oh yeah, don't get me wrong, tons of buildings are being made without continuity. I'm not saying that they are being made continuous, I'm saying they should be. And that's sort of like what you see in passive house, like you're not gonna pass, you know, passive house certification without having continuous layers, right? But you can build a code build house without continuous layers, right? Because you're looking at different metrics there.
Well, but the vapor control layer is, it's not as important, it's not gonna be reflective with your blower door testing, right?
It may
Because that's
or
your
may
air
not, it's sort of like, the vapor control is looking at how moisture's moving through, and then the air control is really what the blower door is testing.
Right.
Those may or may not be the same materials at any given part of the
Right, but I'm
wall.
saying we don't have a test that you can do on your building to say you've addressed the vapor control.
I see. No, that would just be based on material characteristics. So that's like when it's modeled, that's what they're doing, right? So they have metrics for, okay, you're using OSB here, we've assigned it that perm rating, so this is how that's likely to behave based on what we see in the model. You're using, you know, vapor open membrane on the outside, that has this perm rating, that's how it's gonna react. So in some ways, it's sort of theoretical from that standpoint, but it's all based on those perm ratings and how those interact with the building system. But no, we do not have like a blower door test for vapor control. Yeah.
All right, unfortunately, we've run out of time, but I hope we can continue this discussion afterwards. But thank you so much, John, for joining us.
Thanks for having me.
So your email is up there, the presentation.
Yep.
Yeah.
And I have cards over there.
Your cards over here. We still have food back there for people who are here. People online, thank you so much for joining us. We'll be sending out more information, and we hope to see you all at future events. Thank you so much.
Thanks, everybody.
Good night, everybody.